Okay, so here we are looking at another one of my rat's nests of wiring. This time it's the ALU. So it's the Arithmetic and Logic unit for my home-built 6502 CPU. As ever, I've made it on one of these 10 by 10 PCBs that I've had manufactured. And so here's the bare PCB. How this thing works is that the minimum order quantity is 5, so I've got 5 of these. And I've then soldered in the socket, plugged the chips in, and I've got the ALU. So this board is basically this piece in the middle here. So the ALU is at the heart of it here with its 2 registers. I'm going to call that the in A register, the in B register, and the result register here. So you can put 2 numbers in, 8-bit numbers, and get a result from doing whatever mathematics sums or whatever you do in the ALU. You can get the result out here. Now I've only got binary displays on these at the moment because the first things I want to look at with my ALU are binary logic operations like and, or, not, etc. The rest of all this confusing maths, well, I've got a display at the back here for displaying numbers in decimal. So you can get it's a 7-segment LCD display, so I can publish numbers out onto that, so we don't have to just look at them in binary. At the front here, I've got some switches for putting numbers into the registers. So let's say we put 4 of those switches up and 4 of them down. We can slap that value, which we see as 240 in decimal, into the AU register here. So the ALU holds onto the data from the data bus. It works with the data on the central data bus of the CPU, which is flowing from these keys here through this little buffer that I've had to put in so that the keyboard doesn't sit permanently hogging the data bus. It flows through the bus, through here, and up to this screen here so that you can see it in decimal. So any number that we publish onto the bus, we can see in decimal. The keys over here are to do with publishing and storing things in various different registers. So this key number 1 publishes the keyboard onto the data bus. Whatever I put on the data bus gets published, well, whatever I put on the keys gets published onto the data bus when I press this button, and you can see it converted. So this value here in binary is 243 in decimal. Now the ALU is quite a complex beast and it requires quite a few configuration settings. So I've got these switches over here, 1, 2, 3, 4, 5. The 5 right hand ones are used to configure the ALU, the different modes of operation of the ALU, and the far left one is carry. So that's carry in, sending carry into the ALU, and I've got an LED here so that we can see carry coming out of the ALU. I'll talk about carry when I get onto operations that involve carry, but I'm going to start with simplified ones that don't. What you're probably most interested in is how is this ALU made? Well, the 2 key components are these 74HC181s. There's 2 of them, and they are 4-bit ALU on a chip, basically 74 series ICs. So you get a 4-bit ALU here, a 4-bit ALU there, combine the 2 together to get an 8-bit ALU. All this side is concerned with putting things into the A register. This chip is concerned with putting things into the B register, and these ones are concerned with getting the result out, because there's a little bit of complexity that I've built in order for me to get the maximum value for money out of those ALUs. Now the instructions on how the ALU is configured is quite a confusing chart of things. This is taken from the ALU's data sheet. You can do 16, in fact 32 different functions with this ALU. Most of them are quite bewildering and I'm not entirely sure why you'd ever need them. So I've kind of simplified things a little bit, and for the purposes of this video I'm just going to do these instructions here. So what I've got here is 7 different 6502 opcodes. So these are instructions that you could give to a 6502 CPU, and or exclusive or and 4 rotates. And I'm going to try to work out, or I think I've already actually worked out the settings, the configuration settings that you need in the ALU in order to get those things to take place. So let's go through them then. The first one is AND. So what we're going to do is we're going to logically AND 2 things together. So in the 6502 you might have the A register and a value in memory, and you want to AND together the A register and a value in memory. So let's say, well, first of all, We have to look this up on my chart where I've already worked this out. So the 5 configuration flags are on, off, on. So what do we need? On, off, on. I've already got it set to that, so it's great. So I can go to AND mode and hopefully do an AND operation using the 2 registers. So we're going to AND A and B. Now I've called them A and B as the A and B inputs to the ALU. They're not actually registers that you have in the 6502, so it's not the accumulator and some kind of weird B register. They're just the inputs to the ALU. So what I want to do then, if I put in a value, let's pick a nice on off pattern, because I know that that is a value of 170. So I'll select 170 on my keyboard, and I can publish it onto the data bus by pressing switch 1. I can publish it into A. So while I'm holding down switch 1 by pressing switch 7. So now I've published the value on off into this set of, well, into the A register, and it's displayed on these lights here. And I'm going to AND that with 4 switches on, 4 switches off, which is, what's that value? 240. So we can publish that onto the data bus and store that in the B register by pressing switch 8. So there we go. We've managed to transfer A into the A register. We've got one value, and B register we've got the other. And then the ALU is wired through a sort of a private bus. So you don't need to publish anything. You just need to press the store button, which I've got on switch 9, to get the ANDed value of those two ANDed together. So that and that gives me that. So AND, of course, is where any light that's on in the same position in both of these will be on here. So that one and that one are both on, and anywhere either one or none of them are on will be off in this one. So this this bit 1 here is on in A, it's off in B, so it's going to be off in the result. And you can publish the result with switch 2. So we see the result published out onto the data bus. So we know that this value and this value comes to this value. So the ALU has performed the AND operation. Now, of course, the OR operation is a pretty similar kind of thing. So the configuration for this one is M, which means it's in logic mode. So M on means it's in logic mode. And then we want on, off. And this should perform an OR operation. So we've got this value in A, this value in B. Let's do an OR operation. And OR is, of course, where any of the lights are on. If it's on in this, in A, or it's on in B, it comes on in the result. So this time, the very lowest bit, bit 0, is not on in either of those. So it's off in the result. But bit 1 is on in that one, so it comes on in the result. And bit 7 is on in both of them, so it comes out in the result. So we've managed to do an OR. So we can publish that as a decimal number, and that's 250. So that's 2 of the 6502 operations which I know my ALU can do. The next one's exclusive OR, which they call, in 6502 language, they call EOR, but I think XOR is a much better name. So that is on, off, on, off. And in all of these operations, the carry flag doesn't come into it because this is just simply binary. So we've got our values here, and we can get the XOR of it. So XOR is wherever the two are different. Whenever the 2 bits are different, they'll come on. Wherever they're the same, they'll go off. So bit 7 is on, and it's on there, so it'll be off in the result. Bit 1 is on there and off there, so it'll be on in the result. So that is the kind of exclusive OR is sort of the difference operation. It tells you the difference between the two. It lights up whichever bits are different. And one thing that's puzzling in 6502 assembly language is there's no NOT operation. There's nothing to get the inverse of a number where you turn all the 1s to 0s and the 0s to 1s. But there's a little trick to get around this. If you take a value, let's say this value here, and we then put 255 into B, so publish 255 and store it in B, and then do XOR, we get the opposite of the value. So that's the input value, and that's the NOT of the value. Let's choose a different one that's a bit easier to see. We'll put 3 bits on. all the bits off, and yeah, let's put 3 bits on and 5 bits off. So we'll put that in A. We'll do the XOR, we'll XOR it with 255, and we get 3 bits off and 5 bits on. So that is kind of a little backdoor way of getting a NOT, even though there isn't a NOT operation in 6502 assembly language. So this should start giving you a clue about how the CPU that I'm making would work to run an instruction. So if we typed in an ASL, which is an arithmetic shift left operation, so we type in that command, the control unit in the CPU would have to look up that in its table of control bits, and it would have to have, oh look, 0, 1, 1, 0, 0. So that's 0, 1, 1, 0, 0 is the configuration that I need in order to run an ASL command through the ALU. So let's do that then. So this is a shift left, where these are the bits of the number. It shifts a 0 in on the right side, it shifts all the bits to the left, and carry pops out at the end. So this is the first operation where we've actually got some carry taking part in it, and this LED down here is the carry out, and it's not very bright, so I'm going to put my mug there to cast a shadow over it. There it is. There you go. Does that help? Okay, so I've got my mug casting a shadow over the carry bit. So let's run then the arithmetic shift left command. So to do that, let's put something, it's going to shift the answer. Whatever we put in, it's going to shift it to the left. So let's put something that's mainly right heavy. So let's put in a pattern like this. So we've got 2 bits on at the end there, and then a gap, and then 1 bit on. We want that to go in and shift over to the left. In this particular instruction, carry isn't used as an input, so we don't feed carry in, but we do get carry out. So that means I actually have to set carry to be off in order to get this instruction to work. And the carry flag, annoyingly, works on a reverse logic. So putting it up turns carry off, which is a little bit annoying. And one of the things that's strange about this ALU is that if you work in the mode where the numbers are positive going logic, the control signals are negative going logic, and putting your carry in backwards is really irritating. So I think what I'm going to do in my next revision of this ALU board, I'm going to put a NOT gate for the carry coming in and a NOT gate for the carry going out, so I can use positive going carry. And I do need another revision of this board, because you can see by these bodge wires here I made a couple of slight mistakes when I was making the board. Right, so let's do this shift left operation then. So we'll put that value in, and we should expect to see it shifted to the left, and if a bit gets shifted out the left, it should come out onto the carry light. Now register B doesn't feature in a shift left, so I'll just clear that out. It's not involved at all, so I'll just clear it to get it out of the way. And so if I publish our current value into register A, and then press this to perform the operation, what's happened is the data has all been shifted slightly to the left. So let me just check this in binary then. So it's 11, I've put a value of 11 in, and I can publish the result, and it's been shifted left to 22. And because of the magic of binary, if you shift something to the left by 1 place, it actually doubles the number. So I've converted 11 into 22. And there's no carry coming out because nothing shot out the left-hand end of the byte. So now let's transfer the result back in to A. So we'll publish the result onto the data bus and store it in A. So now I've moved my, where's publish A? We can't publish A actually. There isn't an option to publish A, but I've moved the 22 into there. Let's do another shift left. And so now it's moved slightly over to the left. It's a little bit, can you see that? Yeah, I think you can. But we can check the value anyway. So we went 11, we went 22. So now we're on 44. So let's now publish the 44, slap it back into A again, and shift it to the left one more time. Publish it again, slap it back into A. Did I do that? No, press the wrong button. And shift it left another time. And we'll publish that and slap it back into register A. And this time when we shift it left, the carry is going to come on. In fact, the ALU already knows the carry is going to come on because I've got this value buffered to come out, but the carry comes out straight away. So there we are, we've shifted it left and we've popped one bit out to the side. So we'll publish that value again, put it back into A and shift it right again. And we can carry on publishing it and shifting it into A, sending it up to the right. So that is ASL, arithmetic shift left. And there's a roll, I don't know why it's called roll, rotate to the left, I guess. And the only difference here is that the carry flag, any carry flag that you put in, gets put in the right hand side as the shift takes place. So if we start with that value again, put that into A, this time we have to actually set the carry flag. And now if we shift to the left, yes, if we shift to the left, we've moved everything to the left and we've put a carry in on the right. So if we then, I'm confusing myself now, if we publish that through to A and rotate again, we keep getting bits fed in at the right. So it's exactly the same operation, shifting to the left, but carry gets fed in on the right hand side. Good, so I can see how I can do 1, 2, 3, 4, 5 of the instructions for 6502 assembly language, but there's 2 more of them. LSR, very confusingly, but that's logical shift right, and ROR, which is rotate right. These rotate bits to the right, and this ALU does not do rotates to the right as one of its instructions, so I've had to get round things a little bit. Yes, I just have to swap over one of the wires here, and that puts my ALU into reverse mode. So what I do is, the data comes in, I switch it over, I rotate it to the left, and then I switch it back again, and the net result of that is the same as rotating it to the right. So because this CPU doesn't have a rotate right function, because this ALU doesn't have a rotate right function, I can sort of fake one. So what I've done is I've got 4 different ways of getting data in. There's the normal way of getting data into A, there's a reversed way of getting data into A, and then there's 2 others for some other sneaky instructions that I've got later. They go into the CPU, they get shifted to the left, and then I've got a way of flipping them back again in order to get them out the end. So this is a slightly more complicated one, but if we put that value, well, that'll be a rubbish value for putting into rotate right, won't it? So let's put there. Yeah, that's a good value for rotating to the right. So we've got 2 bits on, 2 bits off, 1 bit on, 3 bits off. We'll store that in A. So you can see when it comes into A, it's been reversed, and then when we do the shift, we've now shifted it one place to the right. Now I'm doing the wrong one here. I'm doing the rotate right with the carry coming in. So you can see how that's brought the carry in because the carry's switched on. So I'll turn the carry off, and we'll do the other operation, which will rotate R. So we want to put this back into A. So we publish it, shove it back into A. It comes out reversed in A, and then we rotate it to the right again. And so now we've rotated it over to the right and we've fed no carry in on the right. And if we feed it into the A register again and rotate it, we feed it into the A register again and rotate it, the bit that dropped off the right hand side has come out on the carry flag there. Feed it into the A register again and rotate it. No carry dropped off that time. Feed it into the A register again, rotate it, no carry dropped off that time, and then this time as it rotates it out the end, carry will drop out the end there. So we'll put it into A and rotate it again, and we've got carry popped out the end. Put it into A and rotate it again, put it into A and rotate it again. So we've rotated the whole of the number right out of the 8 bits. We've sort of rotated the whole of the 8 bits right through. Okay, so that's 7 instructions that I'm quite confident I would now be able to make my CPU perform if I connect up the controller to the ALU should be able to do these instructions, and they're much more interesting. Previously, the instructions I've been able to do with my CPU have only been about moving things from one register to another. But I think once you can start combining numbers together, I think the whole thing becomes about 1,000 times more interesting. So I think I'll leave it there for this video, and I think in the next one I'll go through the sort of things you expect an ALU to do, such as add and subtract.